Good morning, guys. This is Rashiyas from Mathematics Department, and I'll be handling Fourier series for you this semester. And before starting up with this, you have come across Taylor series, Maclaurin series, logarithmic series, exponential series, binomial series, and so on. And this is one such series which is used in many engineering problems, and this can be used to expand a given function in a series containing cosine and sine terms, which belongs to a class of functions called periodic functions. And the definition for periodic function is given below. So we'll start off with the definition of periodic functions. A function f from R to R is said to be periodic if there exists a positive number t such that f of x plus t is equal to f of x for all x belong to R. The number t is called a period t of the function f. So here, if the given function f of x, if it is equal to f of x plus t, then this t is called the period t and this function is called periodic function. And to be more clear, let's take some examples. Sine x plus 2 pi is equal to sine x. So here sine x is a periodic function of period 2 pi. Similarly, cos x plus 2 pi is equal to cos x. Therefore, cos x is a periodic function with period 2 pi. And one more example. If f of x is equal to k, then f of x plus 2 pi is also equal to k, a constant function. This means f of x is equal to f of x plus 2 pi, and therefore f of x is a periodic function with period 2 pi. And when you talk about the graph of periodic function, see, consider this sine x. See, for the sine x, there is a sinusoidal wave. Okay, it starts from 0. So there will be one up and one down, downward curve. And again, that curve repeats after a certain interval of time. And that interval here is 2 pi. And after 2 pi, again the curve goes up and down. And again, that interval will be 4 pi. So, at every interval of 2 pi, the curve or the graph repeats. So, this type of function is called periodic function. And for sine, the period is 2 pi. Okay. Moving on to the property of periodic function. A linear combination of periodic function having period t is also periodic of period t. That is, if f and g are two periodic functions of period t, then function h defined by h of x is equal to a into f of x plus b into g of x. That is, h of x is a linear combination of two periodic functions f and g, is also periodic function of period t. So this is one of the property of a periodic function. Let me repeat. There are two periodic functions f and g of same period t. Then the function h, which is the linear combination of the two periodic functions f and g, is also a periodic function of the same period t. where a and b are constants. So this is one of the property of periodic function, guys. Okay. And moving on to trigonometric Fourier series. See, Fourier series is also known as trigonometric Fourier series. Okay. So here the infinite series a naught by 2 plus summation n equal to 1 to infinity an cos n pi x by L plus summation n equal to 1 to infinity bn sin n pi x by L is called the Fourier series or trigonometric Fourier series for the function f of x in the interval a comma a plus 12, where a naught, a1, a2, etc. up to a infinity, b1, b2, etc. up to b infinity are called the Fourier coefficients of f of x. Okay, and here what about this a naught, an, and bn? They are formulated by equation 1, 2, and 3, and these three formulas are termed as Euler's formulas. Okay, where a naught is given by 1 by L integral a to a plus 2L f of x dx, an is equal to 1 by L integral a to a plus 2L f of x cos n pi x by L dx, n running from 1 to infinity, and bn is equal to 1 by L integral a to a plus 2L f of x sin n pi x by L dx, n running from 1 to infinity. These three are known as Euler's formulas. Okay, and here in this class, we'll be deriving Euler's formulas. That is, we'll be deriving how you got a naught, an, and bn. Okay. And before starting up with the Euler's formula, we need some basic results. So we'll note these basic results, which are very necessary to derive the Euler's formula. Okay. The first formula, integral a to a plus 2L dx is equal to 2L. The second one, integral a to a plus 2L cos m pi x by L dx is 0. And integral a to a plus 12 sin n pi x by L dx is equal to 0. These are all taken from reduction formula, okay, which you have learned in previous semesters. Third one, integral a to a plus 2L cos m pi x by L sin n pi x by L dx is equal to 0 for all integers m and n. Integral a to a plus 2L cos n pi x by L cos n pi x by L dx is equal to integral a to a plus 2L sin n pi x by L sin n pi x by L dx equal to 0. Okay, so both integrals goes to 0, and here the last one, cos square m pi x by L integral of sin square m pi x by L is equal to L between the limits a to a plus 2L. See here, when this n becomes equal to m, then that becomes cos square m pi x by L. Okay, so if m is not equal to n, then this integral will be 0. Suppose m is equal to n and n is equal to m, then that becomes cos square m pi x by L, and the value here is L. The same thing holds for sine also. Okay, so this is all about the basic results which we need to derive Euler's formula. So let's start up with the derivation of Euler's formula. Okay, see, we have the Fourier series expansion for f of x to be a naught by 2 plus summation n equal to 1 to infinity an cos n pi x by L plus summation n equal to 1 to infinity bn sin n pi x by L. We'll name that as first equation. Okay, now we'll find what a naught is. Okay, now what we'll do, we'll integrate this one with respect to x from a to a plus 2L. Okay, so integrating this equation 1 with respect to x between the limits a and a plus 2L, we have this equation. Okay, and by the basic result, this term and this term vanishes. Okay, we are left with this term and this term. So here you can see a naught by 2 into integral a to a plus 2l 1 dx is 2l. Okay, and this thing is 0. The second and third term vanishes due to the basic results, and here 2 and 2 will get cancelled. And since we are interested in finding what a naught is, we'll cross multiply this L the other side. So that becomes 1 by L integral a to a plus 2L f of x dx. So this is how we'll find a naught, the first Euler's formula. So let's move on to second Euler's formula, how to find an. So to find an, we'll multiply both sides of 1 by cos m pi x by L, where m is a fixed positive integer, and integrate with respect to x from x is equal to a plus 2a. Okay, so here we'll multiply in such a way that the remaining two terms vanishes. Okay, so, and this an term will retain as it is, and the other two terms, that is a naught term and bn term, vanishes. So in such a way that we'll multiply. So here we are multiplying it by cos m pi x by L, so that the first term and the last term vanishes. So this is how we'll multiply by cos m pi x by L and integrate with respect to x between the limits a and a plus 2a. So this is how we'll integrate, and finally it looks like this after integrating. And according to that basic results, this will vanish, this term will vanish, okay, and also this term will vanish. And the left out thing is this. See, actually this also will vanish when m is not equal to n. When n is equal to m, that becomes cos square m pi x by L dx, and that integral value is equal to L. Okay, so here you can see, guys, see, yeah, the first term and last term have vanished, and you are left with this an term. And here what I've done is I've taken this term outside, where actually here the n is running from 1 to infinity. Okay, at one particular point n becomes equal to m. Okay, and that n equal to m I have taken out of the summation and I have written it separately. Okay, remaining things I have left it here only. So I have written this in bracket, where m not is equal, where m not equal to n, this term, where m becomes equal to n, then that becomes cos square m pi x by L dx. So here when m not equal to n, this whole thing goes to 0. And here this becomes L. Okay, so this is how you will get am into L. Since I'm interested in finding what am is, I'll cross multiply this L the other side and I'll get like this. And changing m to n, I'll get what an is. Okay, an is equal to 1 by L integral a to a plus 12 f of x cos n pi x by L dx. And this is all about the second Euler's formula for an. Okay, similarly, we'll find out the third and the last Euler's formula, that is for bn. To find bn, multiply both sides of 1 by sine m pi x by L, where m is again a fixed positive integer, and I'm integrating with respect to x from a to a plus 2a. So after multiplying by sine m pi x by L and integrating with respect to x between the limits a and a plus 2l, the equation 1 looks like this. Okay, and here this term, first term, a naught term and an term will vanish, and here only this term retains as it is. Okay, and here when m not equal to n, this term also will get vanished. This term exists only when m is equal to n. Okay, so here I have again taken that n equal to m term outside. So here also n is running from 1 to infinity. At one particular point n becomes equal to m, and that term I have taken outside the summation and remaining terms I have written it here. So this condition m not equal to n, I have written it here, and for m equal to n, I have taken it separately out of this summation. Okay, and here this will vanish according to the basic result, and this becomes sine square m pi x by l, where the integral value of sine square m pi x by l is equal to l by the basic result, and b it's equal to bml. Since I'm interested in bm, I'll cross multiply this l the other side, and I'll get 1 by l integral a to a plus 2l f of x sine m pi x by l dx. Changing m to n, we get bn is equal to 1 by l integral a to a plus 2l f of x sine n pi x by l dx. Therefore, we have proved all the three formulas of Euler's formula. Okay, so let's start up with the special cases. There are some 4 special cases. Okay, we'll go through it. First case, suppose a is equal to 0. Then f of x is defined over the interval 0, 2l. Actually, in general, the interval is a to a plus 2l. Since a here is 0, it is 0 to 0 plus 2l or 0 to simply 2l. And now the Euler's formula 1 to 3 becomes a naught equal to 1 by l integral a to a plus 2l becomes 0 to 2l f of x dx. See here and all, just only the limits, upper limit and lower limit gets changed. Okay, instead of a to a plus 2l, that becomes 0 to 2l. That's it. Okay, and now moving on to the next case. Suppose a is 0 and l is pi. Okay, here both the Euler's formula as well as the Fourier expansion changes. Okay, when a is 0 and l is pi, your a naught will be 1 by pi integral 0 to 2 pi f of x dx. So here your f of x is defined over the interval 0, 2 pi. Okay, see here, this is for a is equal to 0 actually, and this is for a equal to 0 as well as l equal to pi. So you just substitute l equal to pi here in this previous case. Okay, you will get for 0, 2 pi interval. Okay, this is how it looks like. And again, when you have change for both a and l, your Fourier expansion also will change. F of x is equal to a naught by 2 plus summation n equal to 1 to infinity an cos n pi x by l becomes nx because l is pi. Okay, and plus summation n equal to 1 to infinity bn sine n pi x by l will be just sine nx because pi and pi will get cancelled. And this is the Fourier series expansion of f of x over the interval 0, 2 pi. So this is all about the second case. So we'll move on to the third case. Suppose a is equal to minus l. Then f of x is defined over the interval minus l, l. And a naught here is equal to 1 by l into integral minus l to l f of x dx. Second one, an is equal to 1 by l integral minus l to l f of x cos n pi x by l dx. See here, only the limits are getting changed. Actually, in general, the limits were a to a plus 2l. Here, a is minus l, therefore minus l to minus l plus 2l, that is l. So minus l to l. So here, only the limits get changed because there is only change in a. If you change both a and l, not only the Euler's formula, but also your Fourier expansion gets changed. Okay, see here. Yeah, the last case, suppose a is equal to minus pi and l is equal to pi, then f of x is defined over the interval minus pi, pi. See, as in go on giving the values for a and l, you will get the Euler's formula or Fourier series expansion for different intervals. Okay, and here you have got 3 different Euler's formula, a naught, an, and bn for the interval minus pi, pi. Okay, And again, since there is a change in both A and L, there is a Fourier series expansion over the interval minus pi comma pi. That is f of x is equal to a naught by 2 plus summation n equal to 1 to infinity an cos nx plus summation n equal to 1 to infinity bn sin x. So this is all about the introduction for Fourier series and derivations of Euler's formula and the 4 separate cases. Okay, so this is all about today's class, and we'll meet in the next class, guys. Thank you.